Ever wonder how AI is getting so good at like creating those lifelike images? Or even predicting those really complex events?
Right.
Well, today we're diving into a whole stack of fresh off the press research papers
Fresh.
from arskv.org,
Right from the source.
all published
Yeah.
just today,
Literally today.
exploring those very possibilities.
Yeah.
Buckle up because things are about to get
It's going to be a wild ride.
interesting.
Yeah, and it's not even just the applications that are advancing. We're also seeing breakthroughs in the fundamental theories behind AI.
Like this paper, Random Sparse Lifts.
Ooh, that's a good one.
It proposes a completely new way to design neural networks, which are essentially the brains of AI models.
Yeah, the really exciting thing about this approach is it uses this concept called gradient flow, and that actually can guarantee learning success. And as these networks grow larger with more parameters, they can actually achieve near-perfect accuracy even without those massive data sets that we usually need for AI training.
So you're telling me we might not need mountains of data to train AI anymore?
Potentially.
It would be a huge shift.
I know, right? It really dives deep into the mouth. It uses concepts from random graph theory and also a field called algebraic topology.
Oh, yeah?
So basically using shapes and structures to understand how these networks learn.
Okay. My brain might need a moment to process that.
It's pretty heavy stuff.
Yeah. But the takeaway is that these large, sparsely connected models could be a game changer for making AI more efficient and less data hungry.
Way more efficient, much less data.
Okay.
Yeah.
Let's move on to another paper that caught my eye. Function space optimality of neural architectures. This one seems to be tackling the underlying math of AI and how it impacts what these models can actually learn.
That's right. This research looks at the functions AI models can perform, like recognizing patterns or making predictions. Think of it as like matching the right tool for the job. If you want an AI that excels at a specific task, you need to understand how its structure affects what it can learn. This paper introduces these new mathematical frameworks called spaces that could unlock even more possibilities for designing AI models with specific capabilities.
So it's like giving AI architects a whole new set of blueprints to work with.
Exactly. That's a great way to put it.
Fascinating. Now let's talk about AI analyzing those complex relationships in data, like social networks.
Okay.
This paper on multi-layer networks, flexible inference in heterogeneous and attributed multi-layer networks,
Oh yeah, this one's really interesting
caught my attention.
because it uses a probabilistic generative model. Imagine the AI is like trying to understand the underlying process that created this web of connections in a social network. It's not just looking at the links, it's trying to figure out why they exist.
So it's like a digital detective,
Yes.
piecing together the story behind the data.
Precisely. And it uses something called a Bayesian framework to make sense of it all. What's really cool is this model's flexibility. It can be used for all sorts of data, from social networks to financial markets.
Now that's what I call adaptable. Speaking of cool applications, this next one. A multimodal data set for enhancing industrial task monitoring and engagement prediction is all about robots and humans working together.
This research explores the potential of multimodal learning. So that's when AI can process different kinds of data at once. In this case, they're using video depth sensors and even data from inertial measurement units, or IMUs, which are like the motion sensors in our phones, to monitor tasks and even predict a human worker's level of engagement.
Wait, so it's like the AI can sense if you're getting bored or frustrated with a task?
Yeah, kind of creepy, right?
That's incredible.
It could be a game changer for safety and productivity in industrial settings.
Yeah.
Imagine an AI coworker that can tell when you need a break or if you're struggling with a particular task.
Wow.
Yeah.
Okay, on to a topic that seems ripped from the headlines. Deepfakes.
Everyone's talking about them.
It's getting harder and harder to tell what's real and what's fake. This paper, Improving Zero-Shot Object-Level Change Detection, looks at how AI can spot those subtle changes in images
Right.
that could indicate a deepfake.
Deepfakes are a growing concern, so being able to detect even minor alterations is critical.
Yeah.
This research utilizes visual correspondence, the relationship between objects in a scene, to train the AI. This helps it understand where objects have been added or removed, improving accuracy and reducing false alarms.
So it's learning to see the world more like we do, understanding those spatial relationships between objects.
Yeah, exactly.
That's impressive. But what about specifically detecting deepfakes?
Well, the researchers behind HFMF, hierarchical fusion, meets multi-stream models for deepfake detection. They've developed a sophisticated framework that uses two stages to identify fake images and videos.
Okay, break it down for me. Hierarchical fusion, multi-stream models. It sounds like something out of a sci-fi movie.
It might sound complicated, but the concept is fairly simple. Hierarchical fusion combines the insights of different AI models like vision transformers and convolutional networks to create a more comprehensive analysis of the image.
So it's like getting multiple expert opinions and then combining them.
Precisely.
Hmm.
The multi-stream aspect focuses on extracting different types of information from the image, such as object-level details, and then merging those findings to make a more informed decision about whether or not the image is a deepfake.
Now let's talk about AI actually creating images. This research on Stargen, a spatiotemporal autoregression framework with video diffusion model for scalable and controllable scene generation, sounds like something straight out of a science fiction novel.
This research uses a pre-trained video diffusion model to generate scenes in a method called an autoregressive manner. Essentially, it builds the scene piece by piece, ensuring each new element fits seamlessly with what's already there.
So it's creating a whole coherent scene that evolves over time,
Yes.
rather than just a random image.
And the impressive part is the level of control it offers. You can guide the generation specifying camera angles, object placements, and even the overall style of the scene. The possibilities for creative applications are immense.
This is blowing my mind. But what about the realism of these generated images? Don't they sometimes have weird glitches or artifacts?
That's a common problem, and this next paper, Struxt SR, Refuse Spurious Details in Real-World Image Super Resolution, tries to solve it. It introduces a method called structure-aware screening, which acts like a quality control expert, filtering out those unrealistic details that often plague AI-generated images.
So it's refining the details to make the image more believable.
Precisely. This is a crucial step in making these images suitable for professional use in fields like advertising, film, and even scientific visualization.
This deep dive into AI image generation has been wild. Let's switch gears and explore the world of language. There's been a huge trend towards larger and larger AI models for language processing, but this paper, Small Language Models, SLMs, Can Still Pack a Punch, argues that smaller models can be just as effective, if not more so.
This research challenges the idea that bigger is always better in AI.
Right.
They explored SLMs with 1 to 8 billion parameters,
Wow.
which is tiny compared to some of the massive models out there. And guess what? They found that these smaller models can achieve comparable or even better performance on various tasks.
So it's about finesse, not just brute force. Why are these smaller models gaining popularity?
Well, for one, they're much more efficient. They require fewer resources to train and run. This makes them more accessible to researchers and developers who don't have access to massive computing power. Think about it. This could democratize AI development.
Makes sense. Levels the playing field a bit. Anything else?
Smaller models are also easier to understand and interpret. With fewer parameters to analyze, it's easier to see how the model is making decisions, which is critical for building trust and ensuring they are being used responsibly.
So smaller models are more efficient, accessible, and potentially more trustworthy.
Yeah.
Now on to a paper that really piqued my interest. Language-inspired relation transfer. It explores how AI can learn new concepts with just a few examples, just like humans do.
This research focuses on something called few-shot learning, where the AI has to generalize from just a handful of examples. The key here is using language descriptions to bridge the gap between what the AI already knows and what it needs to learn.
It's like giving the AI a crash course on the new concept.
Exactly. This research proposes a method that effectively transfers knowledge from the language domain, where we have a vast amount of information, text and speech, to the visual domain, where the AI needs to make sense of images and videos. It's a brilliant example of cross-modal learning.
Wow, we've covered a lot of ground already, from the theoretical underpinnings of AI to image generation and language understanding. It's incredible how quickly this field is advancing.
It is mind-blowing.
But before we dive into even more research, let's take a quick break and come back refreshed
Get a snack.
for part 2 of our deep dive.
Sounds good. Welcome back to our deep dive into the cutting edge of AI research. We've been exploring some incredible advancements, and now I'd like to shift our focus to how AI models represent and process concepts.
Sounds intriguing. This seems like a fundamental aspect of AI, how these systems understand and interact with the world around them.
Exactly. And this first paper will look at separating tongue from thought. Activation patching reveals language-agnostic concept representations in transformers. It tries to answer a fascinating question. Do AI models develop a universal understanding of concepts, Or are their representations tied to specific languages?
It's like asking whether an AI's thoughts are limited by its language. Are we getting philosophical here?
Perhaps a little. This research uses a technique called activation patching to investigate this. They take a pre-trained multilingual language model, think of it like a powerful AI translator, and manipulate its internal workings during a word translation task.
Activation patching sounds pretty technical. Can you explain it in a way that even I can understand?
Imagine the AI model as a network of interconnected points. When it processes language, these points, called nodes, light up in a specific pattern, reflecting the model's understanding of the input. Activation patching involves selectively changing these patterns to see how it affects the AI's output.
So it's like poking around in the AI's brain to see how it reacts.
In a way, yes.
Yeah.
What they found is that the model encodes the output language, that is the language it's translating into, before it encodes the actual concept being translated.
So the model first figures out which language to use and then focuses on the meaning. That's kind of how our brains work too, right?
Right. And building on this insight, they could actually change the concept being translated without changing the output language and vice versa by manipulating those activation patterns.
So they could make the AI say the same thing in a different language or say something totally different in the same language? That's wild. What does this tell us about how AI models understand concepts?
It suggests that these models are developing language-agnostic representations of concepts, at least to some extent. Their understanding isn't completely bound to the specific words used in a particular language.
That has huge implications for the future of AI, especially in areas like machine translation. Imagine an AI that can truly understand the nuances of different languages and cultures.
It's a really exciting area of research. Now let's shift gears and talk about a field where accurate translation is critical: survey design. This paper, exploring the potential role of generative AI in the TREE-APD procedure for survey translation, explores how AI can help translate surveys effectively across different languages and cultures.
Surveys are a critical part of so much research. But as anyone who's ever tried to translate anything knows, it can be a minefield. It's not just about finding the right words, it's about conveying the same meaning and intent to a different audience.
Exactly. This research focuses on the TRAPD procedure that stands for Translation Review, Adjudication, Pretesting, and Documentation, which is a framework for ensuring quality translations.
So it's a very thorough process involving a lot of human expertise. How does AI fit in?
This research explores how generative AI, specifically large language models, LLMs, can assist with the TRAPD procedure. Think of it like having an AI that can spot potential translation issues before the survey even goes out to human translators.
So an AI quality control expert, how does it do that?
The researchers use something called zero-shot prompting. They basically give the AI a survey question and ask it to identify any parts that might be difficult to translate accurately or effectively.
It's like giving the AI a language exam. What kind of things can it detect?
They found that the AI is pretty good at spotting potential translation challenges, like phrases or idioms that are specific to one language, questions that might be interpreted differently in different cultures, issues of sensitivity or formality, and even concepts that might not exist in other cultures.
That's really impressive. It's like having an AI cultural consultant that can help ensure the survey is both accurate and appropriate for the target audience. This could be a game changer for researchers conducting cross-cultural studies.
It's another great example of how AI can complement human skills and improve complex processes.
Yeah.
Speaking of complementing human capabilities, our next paper explores the idea of using AI to actually help other AI systems adapt and learn more effectively.
AI helping AI? That's meta. I'm picturing robots teaching each other in a secret lab somewhere.
Well, maybe not quite like that. But this paper, Active Inference for Self-Organizing Multi-LLM Systems, a Bayesian thermodynamic approach to adaptation, proposes a new way to create more adaptive language AI agents by combining active inference with large language models.
Okay, you're going to have to break that down for me. Active inference, self-organizing multi-LLM systems, Bayesian thermodynamic approach. These are some seriously advanced concepts.
It might sound complicated, but the basic idea is to create AI systems that can actively seek out information and adjust their behavior based on what they experience.
So it's not just about passively processing data, it's about actively learning and adapting.
Exactly. And active inference is a way to understand intelligent behavior based on the idea that agents, whether biological or artificial, try to minimize surprise and make sense of their environment.
So it's like the AI is constantly trying to figure out the rules of the game by playing it and seeing what happens.
That's a good analogy. This research proposes using active inference to create a cognitive layer on top of large language models. This allows them to dynamically adjust their prompts, basically the instructions we give them, and their search strategies for finding information.
So it's giving the AI more control over how it learns and adapts. Why is that important?
Large language models are incredibly powerful, but they are limited by the data they're trained on and the prompts they're given. Active inference gives them a way to learn beyond their initial training data, making them more independent and resourceful.
It's like giving the AI the ability to think for itself and learn from its mistakes. What are some of the benefits of this approach?
This research suggests that active inference can lead to AI systems that are more robust, less likely to be thrown off by unexpected changes, more adaptable to new tasks and goals, and more efficient at learning from their experiences.
This is fascinating. It seems like we're moving towards AI systems that are not just intelligent, but also adaptable, resourceful, and constantly learning. Now let's talk about another aspect of AI development, organizing the information that models learn. I imagine that with so much data, things can get pretty messy inside an AI's brain.
You're right, organization is crucial. In this next paper, Shrink the Longest, Improving Latent Space Isotropy with Simplicial Geometry, tackles this challenge.
Okay, latent space isotropy. That sounds like a whole new level of AI jargon. Can you break it down for me?
Think of it this way. The latent space is the model's internal representation of the information it has learned. Isotropy refers to how evenly that information is distributed. Ideally, you want the information to be spread out nicely rather than all clustered together in certain areas.
So it's like organizing a library. You want the books distributed evenly across the shelves so it's easy to find what you're looking for.
Exactly. This research uses something called simplicial geometry, which is a branch of mathematics that deals with shapes and spaces to analyze the structure of the latent space and identify areas where the information is too clustered or unevenly distributed.
So they're using math to tidy up the AI's mental library. What are the benefits of doing this?
Improving the organization of information within the model leads to several benefits. Better generalization, meaning the AI can apply what it's learned to new situations. Improved robustness, making it less sensitive to noisy data. And enhanced interpretability, making it easier for us to understand how it's making decisions.
It's like having an AI that's not only smart, but also well organized and transparent. This research highlights the importance of thinking about the structure and organization of information within AI models. It's not just about having a lot of data, it's about making sure that data is structured in a way that supports effective learning and generalization. Now let's dive into a paper that brings AI into the classroom. This one seems particularly relevant in our ever-evolving education landscape.
This paper, Advancing Personalized Learning Analysis via an Innovative Domain Knowledge-Informed Attention-Based Knowledge Tracing Method, explores how AI can personalize education tailoring learning experiences to individual student needs.
Personalized learning is a hot topic these days. Everyone learns differently, so the idea of moving away from a one-size-fits-all approach is exciting. But how does AI factor into this?
This research focuses on something called knowledge tracing, which involves creating a model of a student's understanding of concepts as they learn. Think of it like tracking a student's learning journey as they progress through a course.
So it's like having an AI tutor that's constantly monitoring the student's progress and adapting the lessons based on their individual needs.
That's a great way to put it. This research proposes an innovative way to do knowledge tracing, using an attention-based method that incorporates domain knowledge.
Domain knowledge.
That means knowledge about the specific subject being taught. It's not just about tracking performance on individual questions, but about understanding the underlying concepts and how they connect.
So the AI is not just looking at the individual test scores, it's understanding the bigger picture of what the student is learning.
Precisely. And by incorporating this domain knowledge, the AI can provide more personalized and insightful feedback, helping students focus on the areas where they need the most help.
It's like having an AI tutor that can not only tell you what you got wrong, but also explain why and how to improve. Now that's personalized learning.
This research shows how AI can make education more personalized, engaging, and effective. And it's important to note, it's about augmenting human teachers, not replacing them. AI can provide the data and insights, but teachers still play a crucial role in designing the curriculum, fostering a love of learning, and building relationships with their students.
Absolutely. Technology should support teachers, not replace them. Now let's switch gears and delve into a paper that explores the intersection of AI and cultural understanding, which seems like a particularly complex area for AI to navigate.
This paper, Halal or Not, Knowledge Graph Completion for Predicting Cultural Appropriateness of Daily Products, dives into the world of halal dietary guidelines and how AI can be used to predict whether a product aligns with these guidelines.
The concept of halal is important to millions of people around the world. But as you said, it can be very nuanced. It's not just about avoiding certain ingredients, but understanding the whole process of how a product is made. How does AI help with this?
This research uses a knowledge graph, which is a way to represent and analyze complex relationships between different entities. In this case, it might include information about ingredients, manufacturing processes, certifications, and other factors relevant to halal guidelines.
So it's not just a database of ingredients, it's an AI that understands the connections between those ingredients and the processes involved in making the product.
Exactly. And by analyzing this knowledge graph, the AI can predict a product's halal status with more accuracy and nuance than simply checking for specific ingredients.
That's really valuable for people who are trying to make informed choices about the products they buy. It seems like AI is becoming increasingly adept at handling complex cultural and ethical considerations. Speaking of ethical considerations, let's move on to a paper that explores how we can make AI more transparent and accountable.
This paper, Robust Counterfactual Explanations Under Model Multiplicity, using multi-objective optimization, tackles a key challenge in deploying AI, ensuring that we understand how the AI is making decisions, particularly when multiple models are involved.
As AI systems become more complex, it's essential to understand their decision-making process. What are counterfactual explanations, and why are they important?
Imagine you're denied a loan by an AI system. A counterfactual explanation would tell you what would need to change for your application to be approved. For example, it might say that if your credit score was 50 points higher, you would have been approved.
So it helps you understand the reasoning behind the AI's decision. That's crucial for transparency. But you mentioned that multiple models can make things more complicated.
Right. Many AI systems use multiple models working together, each with its own logic. This can lead to conflicting explanations that are hard to interpret. This research addresses this challenge by using a multi-objective optimization approach.
Multi-objective optimization. Can you elaborate?
It's like trying to find a solution that satisfies multiple goals simultaneously. In this case, it might involve ensuring consistency across different models, minimizing the changes needed to change the AI's decision, and finding explanations that are meaningful and easy for humans to understand.
It's like finding the perfect balance between accuracy, consistency, and interpretability. This is important work, especially as AI starts to make decisions that impact our lives in significant ways. Now let's move on to a paper that delves into another crucial aspect of AI trustworthiness, explaining why AI models flag certain patterns in data as unusual.
This paper, explaining deep learning-based anomaly detection and energy consumption data by focusing on contextually relevant data, dives into the challenge of understanding why AI models might flag certain energy usage as anomalous.
This is a timely topic as we all become more mindful of our energy consumption. It's not enough to simply know that something is unusual. We need to understand why it's happening so we can take action. How does this research make AI-powered anomaly detection more explainable?
This paper acknowledges that traditional methods for explaining AI decisions like SAP can sometimes be unreliable when dealing with complex data like energy consumption patterns. So they propose an approach that focuses on contextual information.
Context is everything. Like if your energy usage spikes because it's the hottest day of the year and everyone has their AC blasting, that's understandable. But a spike on a mild day would be cause for concern. How does this research incorporate context into the explanations?
They use several techniques to select a background dataset that's relevant to the specific anomaly being explained. Think of it like an AI detective gathering the most relevant evidence to explain why a particular energy usage pattern was flagged as unusual.
So it's not just saying, hey, this looks weird. It's saying this looks weird because of X, Y, and Z.
Exactly. And their experiments showed that this context-aware approach significantly improved the reliability and trustworthiness of the explanations. This is important work for making AI-powered energy management more transparent and actionable.
It's fascinating how AI can be used not only to analyze data, but also to empower humans to make more informed decisions. Now let's shift gears and explore how AI is being applied to manage the enormous computational resources required for training large AI models.
This paper, Prediction-Assisted Online Distributed Deep Learning Workload Scheduling in GPU Clusters, tackles the challenge of efficiently scheduling workloads in large-scale computing environments, especially for training those massive AI models we've been talking about.
It's like trying to coordinate a giant orchestra of computers, each with its own part to play. As these models grow in size, training them becomes more complex and resource-intensive. How does AI help manage this complexity?
This research introduces a new scheduling algorithm called ASRPT, which stands for Adaptive Shortest Remaining Processing Time First.
Okay, that's a mouthful. What's the basic idea?
The algorithm predicts how long each task will take and prioritizes the tasks that are closest to completion.
So it's like a super efficient project manager that's constantly juggling tasks to make sure everything gets done as quickly as possible.
Exactly, and it's specifically designed for the unique challenges of training AI models on multiple GPUs. It considers factors like communication overhead between servers and the complexity of the AI models to make smart scheduling decisions.
This is a great example of AI being used not only to build intelligent systems, but also to manage the infrastructure that powers those systems. Now let's move on to a paper that explores the application of AI in a completely different domain: medical imaging.
This paper, Learned Discrepancy Reconstruction and Benchmark Dataset for Magnetic Particle Imaging, focuses on improving image quality in a relatively new medical imaging technology called magnetic particle imaging, or MPI.
I'm always fascinated by new medical technologies. What's special about MPI?
MPI has a few advantages over traditional methods. It doesn't use ionizing radiation, can capture images in real time, and is particularly good at visualizing certain biological processes. But one of the challenges with MPI is reconstructing clear images from the raw data collected by the scanner. The noise model in MPI, basically the way errors get introduced into the data, is complex and doesn't always play nicely with traditional image reconstruction algorithms.
It's like trying to solve a jigsaw puzzle where some of the pieces are warped or missing. So how does this research improve the process?
This paper introduces a new reconstruction method called the learned discrepancy approach. It leverages machine learning to adapt to the unique noise characteristics of MPI data.
So instead of using predefined rules, the AI is learning how to handle the quirks of this specific imaging technique.
Exactly. And they've also introduced a new benchmark dataset that can be used to evaluate different MPI reconstruction methods. This is crucial for advancing the field and making MPI more widely used in medical diagnosis and research.
It's amazing how AI is being used not only to improve existing technologies, but also to accelerate the development of new, potentially life-saving technologies. Speaking of cutting-edge technology, let's dive into a paper that explores the intersection of AI and quantum computing.
This paper, Learning to Measure Quantum Neural Networks, explores how we can combine the power of quantum computing with the flexibility of machine learning.
Combining two of the most futuristic technologies out there, this sounds like something straight out of a science fiction movie. What's the main focus of this research?
It proposes a novel approach to make the measurement process in quantum neural networks. That's the part where we extract information from the quantum system learnable.
Traditionally, the way we measure quantum systems is fixed, right? But this research is proposing a method where the AI can learn to optimize the measurement process itself.
Exactly. It's like giving the AI the ability to not only learn from the quantum world, but also learn how to best interpret the information it gets from that world. It's a truly groundbreaking concept that could lead to significant advances in quantum AI.
It's mind-boggling to think about the possibilities. This research really highlights the power of AI to transform even the most complex and challenging domains.
Absolutely. And it underscores the point that AI innovation isn't just about bigger models or more data. It's about finding creative ways to apply machine learning to solve new problems and push the boundaries of what's possible. Speaking of creative applications, let's move on to a paper that explores how we can get different AI models to collaborate and work together more effectively.
I'm intrigued by this idea of AI collaboration. It seems like we're moving away from the idea of a single, all-powerful AI and towards a more distributed and cooperative approach. What's the next paper about?
This paper is titled, Facilitate Collaboration Between Large Language Model and Task-Specific Model for Time Series Anomaly Detection. It explores how we can combine the strengths of different AI models to tackle complex tasks more effectively.
This reminds me of how our own brains work. We have different areas specialized for different tasks, all working together seamlessly. How does this research translate that concept to AI?
This research takes inspiration from the human nervous system. Think of a large language model as the brain providing high-level knowledge and insights, while a task-specific model acts like the peripheral nervous system, focusing on the details of a specific task.
So it's like having a team of AI experts, each with their own specialized skills working together to solve a problem.
Precisely. And this paper focuses on the task of time series anomaly detection, which involves identifying unusual patterns in data that changes over time, like monitoring financial markets or detecting equipment failures.
That's an incredibly important task in many fields. But what are the challenges in getting these different AI models to work together smoothly?
One of the main challenges is making sure the models are speaking the same language. Large language models typically work with text and code, while task-specific models might deal with numerical data or other specialized formats. Bridging this communication gap is key for effective collaboration.
It's like trying to get a poet and a scientist to collaborate. They both have valuable expertise, but they need to find a way to communicate effectively.
That's a great analogy. This research proposes a framework called Collate that introduces an alignment module to help translate information between different AI models.
So it's like having an AI interpreter that makes sure everyone is on the same page. What are some other challenges this research addresses?
Another challenge is preventing errors from cascading through the system. If one model makes a mistake, it can affect the others. Collate includes a collaborative loss function, which encourages the models to learn from each other and correct each other's mistakes.
It's like building a system where the AIs can learn from each other's strengths and weaknesses. It's incredible how these researchers are taking inspiration from human collaboration to develop more robust and reliable AI systems. Now let's explore a paper that dives into the realm of predicting the future.
Ah, yes, the age-old pursuit of knowing what tomorrow holds. This paper, Deep Switching State Space Model, DS3 of $3 for nonlinear time series forecasting with regime switching, tackles the challenge of time series forecasting, which is all about predicting future values based on past data.
Forecasting is notoriously difficult, especially when dealing with complex systems that can change their behavior over time. How does this research address these challenges?
This paper introduces a new model called DS333, which stands for Deep Switching State Space Model. It might sound complicated, but the basic idea is to combine the power of deep learning with the flexibility of state-space models, which are mathematical tools used to model systems that evolve over time.
So it's like combining a powerful engine with a sophisticated navigation system to chart a course through the uncertainties of the future.
That's a great way to put it. DS33 is particularly good at dealing with data that exhibits regime switching, meaning it can suddenly change its behavior. Think of things like financial markets during a crisis or weather patterns during a climate shift.
So it's an AI that can adapt to sudden plot twists in the story of the future.
Precisely. One of the key innovations in this research is the use of discrete, latent variables, which act like switches that represent different states or regimes of the system. This allows the model to capture those abrupt changes that can throw off traditional forecasting methods.
It's like having an AI that can switch gears and adapt to different scenarios as they unfold. What are some other advantages of this approach?
The model also uses continuous latent variables to represent the underlying factors that drive the system's behavior, capturing those more subtle and gradual changes that happen over time.
So it's an AI that can see both the forest and the trees, understanding the big picture trends and the smaller details that contribute to them. This is truly remarkable work. Now let's delve into a paper that explores a more fundamental aspect of AI, its ability to learn and solve problems in a way that's similar to human thinking.
This paper, titled Programmatic Reinforcement Learning, Navigating Grid Worlds, dives into the world of reinforcement learning, a powerful approach for training AI agents to make decisions in complex environments.
Reinforcement learning is all about trial and error, right? The AI learns by interacting with its environment and receiving rewards or penalties for its actions. What makes this research unique?
This research focuses on programmatic reinforcement learning, where the AI's decision-making strategy is represented as a program. It's like giving the AI the ability to think in terms of higher-level concepts like loops and conditional statement.
So instead of just learning by rote memorization, it's learning to think more like a programmer. What are the advantages of that?
One of the key advantages is that it can lead to more efficient and generalizable learning. By representing policies as programs, the AI can learn more compact and reusable representations of its decision-making process.
It's like learning a set of tools that can be applied to a wide range of tasks rather than just memorizing a specific solution for each individual problem. But teaching an AI to think like a programmer sounds incredibly challenging.
It is. One of the challenges is developing algorithms that can effectively learn and optimize these programmatic policies. Traditional reinforcement learning algorithms work with simple representations of actions and states. But this new approach requires algorithms that can handle the complexity of higher-level programming constructs.
It's like teaching a dog to solve algebra. What are some of the key contributions of this research?
This paper offers some of the first theoretical insights into programmatic reinforcement learning. It provides limits on how complex these programs need to be to solve certain problems. They've also introduced an algorithm for creating these policies, which is a crucial step towards making this approach more practical.
It's groundbreaking work. It lays the foundation for a whole new way of thinking about AI and its potential to solve problems in a more human-like way. Now let's delve into a paper that explores the theoretical underpinnings of a powerful type of AI model called neural operators.
This paper, Convergence Analysis of Wide, Shallow Neural Operators Within the Framework of Neural Tangent Kernel, delves into the mathematical world of neural operators, which are AI models capable of approximating complex functions and solving a wide range of problems, even those involving partial differential equations.
Neural operators sound incredibly powerful. What makes them unique compared to other AI models?
One key advantage is their ability to handle infinite dimensional data, such as functions and continuous signals. Traditional neural networks are designed to work with finite dimensional data, like images and text. But neural operators can work with more abstract mathematical concepts.
It's like having an AI that can understand and work with the language of calculus. What's the specific focus of this research?
This research focuses on the convergence analysis of wide, shallow neural operators. Convergence is all about whether a learning algorithm can find a solution that minimizes errors. This research explores what happens when we apply a popular optimization algorithm called gradient descent to these neural operators.
So it's about understanding how these models learn and ensuring they find the best possible solutions. What are some of the key findings?
This paper shows that under certain conditions, gradient descent can find the optimal solution for wide, shallow neural operators. This provides a theoretical guarantee that this learning approach is effective. However, the research also highlights the importance of something called overparameterization.
Over-parameterization. What does that mean?
It means having more parameters in the model than data points. While this can lead to overfitting in traditional neural networks, it actually helps in the case of neural operators, ensuring that the learning algorithm converges to a good solution.
So sometimes having a bigger, more complex model can actually be beneficial. It's counterintuitive but fascinating.
Absolutely.
Yeah.
This research is a great example of how theoretical analysis can provide valuable insights into the behavior and capabilities of AI models. It highlights the importance of both mathematical rigor and practical experimentation in advancing the field.
This has been such a fascinating exploration of the latest advancements in AI. From the theoretical foundations to the practical applications, it's amazing to see how rapidly this field is evolving.
And we're not finished yet. We still have a few more papers to discuss, exploring even more cutting-edge research in AI. Join us in part 3 as we continue our deep dive into this exciting field.
Welcome back to the Deep Dive. We've been on quite a journey exploring the latest breakthroughs in AI research, and I'm excited to see what other fascinating discoveries await us in this final part of our deep dive.
We've covered a lot of ground from fundamental theory to real-world applications, and now we're going to delve into some research that bridges those two realms. Let's start with a paper that focuses on decision trees, which are widely used in machine learning for tasks like classifying data and making predictions.
Decision trees are great because they're easy to understand. You can visualize how they're making decisions, but I know they can sometimes be a bit too sensitive to small changes in data, leading to something called overfitting. Is that what this research is trying to address?
Exactly. This paper titled Soft Regression Trees, a model variant and a decomposition training algorithm introduces a new type of decision tree called soft multivariate regression trees, or SRTs for short. These SRTs can handle both categorical and numerical data and are designed to be more robust and less prone to overfitting.
So they're like decision trees with a bit more flexibility, less likely to jump to conclusions based on small variations in the data. How do they achieve that?
Instead of making hard splits based on strict thresholds, SRTs assign probabilities to different branches in each node. This allows for a more nuanced decision-making process, considering multiple possibilities rather than going all in on one option.
It's like the tree is hedging its bets, taking a more probabilistic approach. I like that. But training these more complex trees must be computationally demanding. Does the paper address that as well?
Yes, it does. The paper proposes a new training algorithm that breaks down the problem into smaller, more manageable chunks. This decomposition approach makes the training process much faster and more scalable, especially for those massive data sets that are so common in AI.
So more efficient models and faster training, that's a win-win. It sounds like a significant improvement over traditional decision tree methods. What kind of results did they see with this approach?
The researchers tested their method on 15 different data sets and found that it consistently outperformed traditional soft regression trees in terms of both accuracy and robustness. They also saw significant reductions in training times, making it more practical for real-world applications.
That's impressive. It's a great example of how innovative algorithms can really push the boundaries of what's possible in AI. Now let's move on to a paper that explores a different area of AI generating graphs.
This paper, Learning to Generate Feasible Graphs Using Graph Grammars, tackles the challenge of generating graphs that are not only structurally complex, but also meaningful within a specific domain.
For those who might not be familiar, can you explain what graphs are and why generating them is important?
A graph is essentially a network of interconnected nodes. They're used to represent all sorts of things: social networks, molecular structures, transportation systems, and much more expresses. Generating graphs is important because it allows us to explore possibilities, test hypotheses, and even design new structures or systems.
So it's like having an AI architect that can design new structures or systems based on certain rules and constraints. What's the challenge that this research is addressing?
One of the key challenges is making sure that the generated graphs are feasible, meaning they adhere to the rules and constraints of the specific domain they represent. For example, if you're generating molecular graphs for drug discovery, you need to make sure that the molecules you create are chemically plausible and could potentially exist in the real world.
It's like making sure the bridge you design won't collapse. How does this research tackle the feasibility problem?
They use a novel approach based on graph grammars, which are essentially a set of rules for constructing graphs. Think of them as the building codes for creating graphs. And their key innovation is introducing a domain-dependent coarsening procedure.
Coarsening procedure. Can you unpack that term for me?
Coarsening is like simplifying a graph by grouping similar nodes together. It's like creating a more abstract representation of the graph that still captures its essential features. And in this case, the coarsening procedure is tailored to preserve the specific rules and constraints of the domain.
So it's like making sure the simplified blueprint still adheres to the building codes. Exactly. By incorporating this coarsening procedure, the AI can generate graphs that are more likely to be feasible within the specific domain, ensuring they're not just structurally sound, but also meaningful and relevant.
This research shows how AI can be used not only to generate creative solutions, but also to ensure those solutions are practical and grounded in the real world. Now let's turn our attention to a paper that focuses on a crucial aspect of AI trustworthiness, making sure the AI's confidence in its predictions is aligned with its actual accuracy.
This is a crucial aspect of deploying AI in real-world applications. If an AI model predicts something with high confidence but is frequently wrong, it can lead to mistrust and even dangerous consequences.
Exactly. It's like having a weather forecaster who confidently predicts sunshine, but it ends up raining cats and dogs. You'd quickly stop trusting their forecasts. So how does this research address this challenge? This paper, titled Distilling Calibration via Conformalized Creedal Inference, introduces a method called conformalized distillation for creedal inference, or CDCI, which aims to improve the calibration of AI models, especially those running on devices with limited resources.
Conformalized distillation for creedal inference. Wow, that's a mouthful. Can you break that down for us?
Imagine you have a very complex, high-performing AI model, like a seasoned expert. This expert model is excellent at making predictions, but might not be very efficient to run on a smartphone or other resource-constrained device. So you also have a simpler, more efficient model, like a student who is still learning.
Okay, I'm following so far. We have an AI expert and an AI student. What does CDCI do with them?
CDCI works in two phases. In the offline phase, it analyzes the expert model's predictions and confidence scores to determine how well calibrated they are, essentially how much the model's confidence aligns with its actual accuracy. It then uses this analysis to create a set of rules or guidelines.
So it's like figuring out how to adjust the expert's predictions to make them more reliable.
Precisely. Then, in the online phase, when the simpler student model is running on the device, it uses these guidelines to adjust its own confidence scores, making them more aligned with reality.
That's a clever way to transfer the expert's knowledge to the student without needing to run the complex expert model on the device itself. It's like giving the student a cheat sheet to improve their performance. What kind of results did they see?
They tested this method on various tasks like image classification and natural language processing and found that it significantly improved the calibration of the simpler models. This is a big step towards making AI more trustworthy and reliable, even on devices with limited computational power.
This research is another great example of how AI is evolving to meet the demands of real-world applications. Now let's dive into a paper that takes a more theoretical approach exploring the mathematical foundations of a type of AI model called shallow polynomial networks.
This paper, titled Geometry and Optimization of Shallow Polynomial Networks, takes a deep dive into the world of polynomial activation functions, which are a type of mathematical function used in neural networks. It specifically focuses on shallow networks, which are simpler in structure compared to deep networks.
I remember we talked about activation functions earlier. They're like the engine that drives a neural network, determining how it processes information. What's so special about polynomial activations, and why focus on shallow networks?
Polynomial activations can capture more complex relationships in data compared to some other activation functions. And while deep networks are all the rage these days, shallow networks are still valuable for certain tasks, and their simplicity makes them easier to analyze and understand from a mathematical perspective.
So it's like studying a simpler organism to gain insights into the fundamental principles of life. What kind of insights does this research provide?
This research provides a detailed analysis of the optimization landscape for these shallow polynomial networks. The optimization landscape is like a mathematical terrain that the learning algorithm has to navigate to find the best solution. They specifically looked at how the width of the network, the number of neurons in each layer, affects the difficulty of finding a good solution.
So it's like exploring a mountainous landscape, and the width of the network determines how rugged the terrain is.
That's a great way to put it. And they found some interesting connections between the width of the network and the number and types of critical points, which are like the peaks and valleys in that optimization landscape.
It's like having a map that helps guide the AI through the challenging terrain of finding the optimal solution. What other insights did they uncover?
They introduced a new concept called the teacher metric discriminant, which helps predict how well a network will perform based on the training data. Think of it as a way to assess how teachable a particular task is given the available data.
That's valuable information for designing AI systems and choosing the right models for the job.
Absolutely. This paper also delves into the specifics of networks with quadratic activations, which are a particular type of polynomial function. They provide a complete picture of the optimization landscape for these networks, offering valuable insights into their behavior during training.
This is a great example of how theoretical analysis can deepen our understanding of AI and pave the way for more effective learning algorithms. It's fascinating to see how researchers are tackling these challenges from multiple angles, combining practical experimentation with rigorous mathematical analysis.
I agree. And with that, we've reached the end of our deep dives into the latest AI research from rxevi.org. We've explored a vast landscape of innovation, from theoretical foundations to real-world applications in fields like medicine, energy management, and even the quantum realm.
It's been an incredible journey. It's clear that AI is not just a single technology, but a rapidly evolving field with the potential to revolutionize countless aspects of our lives. As we've seen today, AI is not just about building smarter machines, it's about augmenting human capabilities, solving complex problems, and pushing the boundaries of what's possible.
This deep dive has highlighted some key trends shaping the future of AI, such as the growing emphasis on explainability and trust the move towards collaboration and specialization in AI systems, the need for greater efficiency and scalability, and the boundless potential for creativity and innovation.
If you're as fascinated by these advancements as we are, be sure to check out the show notes for links to the research papers we discussed today.
And we'd love to hear your thoughts. Leave a comment and let us know what insights you found most interesting or what questions you still have.
Thanks for joining us on this deep dive into the world of AI. Until next time, keep exploring, keep learning, and keep asking questions, because the future of AI is being shaped right now and we're all part of the conversation.